there are 4 different situations that are given. And these are what they're calling generic decay diagrams. So the first one looks a little bit like this. And again, we're going to have energy on the y-axis, and on the x-axis, we're going to have atomic mass number over here. So Z versus energy, and we're going to do that 4 times actually, because there's going to be 4 different kinds of decays that we're actually going to be discussing here. There are other decays, but these are the kind of the generic pictures of these things. Okay, so in the first one, we have something at a particular energy, and it's decaying to something at a lower energy, and the atomic mass is going down actually by, if I could actually do this by mass units, the atomic mass is actually decreasing by 2 mass units. So we represent that with a straight line. We then have something that looks like this, where now, see, I'm going to use that same relative scale here. Now, again, the energy is going to go down, but the atomic mass is now going to go up by 1 mass unit. So our slope, here we have a positive slope. Here it's a negative slope, but it's the slope is not as steep as it is here. Here we're going 2 mass units. Well, I should say it's steeper actually, because it's y divided by x. So we have a smaller x value, and here we have a larger x value. So this has less of a slope. That has a greater negative slope than the positive slope of this. Finally, or not finally, but then we have another situation here where the mass decreases somewhat, and then, let me go 1, 2, 3 again, and then, I'm sorry, the energy decreases, and then it makes a bend and goes down to this point here. Okay, so this is a third situation, and then we've got another one here where we start out at 1 energy and we wind up at a lower energy, but there's no change in mass. And if you look at these things, it should be apparent to you that because of the change of 2 mass units, that this represents alpha decay. And the second situation represents beta decay. Now these things are pretty obvious. I mean, we know that once we decay to a smaller nuclide, that we're going to get a change in energy. We're also going to get a change in the Z number. It's going to go down by 2. The mass number will go down by 2 units. And if we look, I'm sorry, this is not the mass number. This is the atomic number. I use the word mass number, but that's not what I meant. The atomic number, or the atomic mass, is going down by 2 units. Here, the atomic mass is going down by 1, is coming up by 1 unit. That's beta decay, and again, the energy is going down. And in this last situation here, there's a change in energy, but no change in mass. And we've seen that is what happens in the case of gamma decay. So we've got alpha, beta, and gamma. And then we have one other thing in here, which is actually positron decay. So this is a beta plus decay. And it has the same net effect as beta minus decay, but the difference that in the end we're actually going to lose 1 mass unit, which is what you'd expect for this. But you might ask the question, why is this drawn with first a apparent loss in mass, in energy rather, and then this change in mass. So we're having the energy going down, and then all of a sudden, the mass, the atomic number rather, is going down after that. So that's might at first glance might be a little bit puzzling. But what this is actually representing, and it makes a lot of sense if you think about it, it always used to puzzle me before I saw these kinds of diagrams, why it was that, we had already talked about this once before, we said that, for instance, that when you have beta decay, what's actually happening is that a neutron is converting to a proton. So that sort of makes sense. A neutron is heavier than a proton. We already saw that. A neutron has a mass of 1.0086 665 atomic mass units, and the proton is only 1.007276. So it sort of makes sense that a neutron goes to a proton. It also produces an antineutrino. So you've got this antineutrino that's being produced. Very, very small mass. I mean, it would probably not even be in the sixth decimal place. So very, very tiny mass. We don't have to consider that. And obviously, there's some energy that's also being produced in the process. Well, with positron decay, what's happening is a proton is converting into a neutron. And when you first look at that and you say to yourself, well, how can something that weighs 1.007276 give rise to something that's actually more massive than it is? And the way that that happens is some of that energy is actually converted into mass. So what we have during this decay process is this dropping down in energy, because that's actually giving us the additional mass that we need to convert the proton into the neutron. And once that happens, then we can get the decay to actually take place. So that's an explanation of why those things look that particular way. Okay, so let's see. So we've got a couple examples in here. There's one in there in which sulfur-35 is decaying to chlorine-35 by emitting a beta particle. This is on page 46. And you're asked to draw a decay diagram, write out the balanced equation, which you can see is just that sulfur-35 is going to chlorine-35, and plus a beta particle, which is minus 1 is the mass number, and the atomic, the atomic mass, the total mass of that would actually be 0. So what you've got there is that balances out, and you've got the atomic mass of sulfur, if you actually look it up, is 34.969032 atomic mass units, and the mass of chlorine is 34.968853. So the total energy of decay is the difference between those two things. And if we multiply that by 931.5 million electron volts, we'll get 0.167 million electron volts. So that is the difference in energy. And that's what we're going to find for that particular decay. We're going to find out that that energy is lost at 0.167 million electron volts. So in this diagram here, that would represent that 0.167 million electron volts. We can also, if we're actually looking at, let's see, if we're actually looking, this is beta decay. Let's see. Why is it talking about positron decay? Oh, okay. So they're actually introducing another example in here. What your book is actually telling you here is what I just was trying to explain to you. The fact that the difference between these two masses is about the mass of an electron. So the small amount of mass that has to be created is about the mass of an electron. and that's what this drop here is representing. It's, in this case, for this particular process, you actually need 2 electrons to be made. So that's giving you 1.022 million electron volts. And for every positron decay, you're going to have 1.022 million electron volts they're going to have to be lost in order to make those electrons that you can actually, so you'll actually be able to have this reaction take place. Another example involving, in this case, an example that actually does involve positron decay is the decay of fluorine-17 to oxygen-17. That's shown at the diagram is actually shown in figure 3.4 on page 47. So you'll see again that you have the fluorine. Just make sure that that's the right, yeah, it is. This is for fluorine-17. So it's got fluorine-17 up here, and there is a positron that is being given off, and the energy here is 1.74 million electron volts, and that goes to oxygen-17. And you can calculate these energies given all the data that's in the example. The total energy of decay is 2.7607 million electron volts. The atomic mass is 16.999132 units, and they're asked to calculate the mass of fluorine-17, and you do that by which is, you're actually calculating the mass of the parent. So you look at the 2.76 million electron volts times 930 times 1 atomic mass unit is divided by 931.5 million electron volts. That gives you a 0.002964 atomic mass units, and that if you add that back to the mass of the daughter, which is 16.999132, you get a total mass of 17.002096. So by calculating what the mass is that you're actually going to be adding onto there, that enables you to go back and calculate what the mass of the parent is. There's another example in here that involves electron capture decay. Now, electron capture decay looks, let's see, where do we have electron capture? Electron capture basically looks the same as, it looks like, when you actually look at the electron capture decay diagram, it looks kind of like for alpha particle emission. Well, it looks more like the negative of beta particle emission, because it doesn't go over 2 units. It only goes over 1 unit. But it has, so I guess I probably should draw that in as well. We have electron capture, E and Z, 1, 2, 3, and so we're going to go from here to here. So in terms of its positive slope, it looks like the alpha decay, but in terms of the fact that there's only a 1 mass unit change, well, it actually, what it really resembles more closely is it actually resembles it resembles positron decay, except it would be like positron decay if you had a straight line going down here. So that's what it really resembles. So it's, there's 1 unit that's changing, but in this case, since you don't have to create anything, there's no, you don't get that drop in energy before this occurs. So it's a straightforward process, because the energy for this is actually going to come from, since it's electron capture, it's the energy is coming from the shell, from the electron that's moving from the shell into the nucleus of the atom, and that's what's going to actually cause this process to occur. So that's for electron capture. And again, you can do the same kinds of calculations. And then you can do multiples of these kinds of things as well. So we have quite a bit of time left, I think. let's see, I don't remember exactly what time I started. I think I'm about 45 minutes in. I do want to stop in a few minutes. I don't want to make this as long as the previous lectures, but I want to call your attention to one other decay diagram that's in here, which is figure 3.6 on page 49. And here what we've got is silicon 32 decaying to sulfur 32. And in this particular case, there's actually two separate beta decays that are occurring. So it's actually showing you multiple. So when you want to illustrate something like this, using a decay diagram, you have to show both decays since it's not a single process. And you show that in this fashion. So we start up here with silicon. It undergoes beta decay, and it goes from silicon 32 to phosphorus 32, which is also radioactive. And so now we've got phosphorus 32 here, and then the phosphorus 32 is going to undergo another decay, but its energy, the energy of that decay is greater. So that's going to, if this represents one unit, one mass unit from here to here, and this would be the second mass unit, which would be down here. But the decay is, the energy differential in the decay is greater, so you can see that the slope is actually changing. So we get a second decay. So we have first decay to here and the second decay to there. And I didn't show arrows on these other ones, but there are actually arrows that are showing which way these things are going. But in this particular case, it's actually showing you that this first decay from here to here represents 1.7107 million electron volts. That's from phosphorus down to sulfur 32. This is sulfur 32. That's the stable sulfur. The first decay here is a smaller one, and that's only 0.224 million electron volts. So that's a much less energetic. But you could actually graph these things. Once you calculated what all the energies are, you could graph these very, very exactly what the energy differences were. And I won't ask you to do anything on an exam that involves you actually having to graph anything. But what I'd expect you to be able to do is to look at these kinds of things, and by looking at these shapes, know what kind of a process was taking place. Is it electron capture decay? Is it beta decay, alpha decay, gamma decay, positron decay? So you should be able to, by the time you've looked all of this over, you should have a pretty good understanding of what each of these processes represents. The last thing here is a decay for a metastable state of bromine 77. So bromine 77 is going to decay through a gamma photon, and it's just going to go from here down to here. And so this is bromine 77, metastable, and it's going to go to bromine 77, which is one of the stable isotopes of bromine. A gamma is produced, and the energy of that gamma is, and again, we would do the same thing. We'd actually have to look up what the mass of the metastable isotope is, which is 76.921494 atomic mass units, and the mass of bromine 77, which is 76.921380 atomic mass units. Multiply that by 931.5 million electron volts per atomic mass unit, and that gives us 0.106 million electron volts, and that is, since it's only a tenth of a million electron volts, that's going to give us 106 keV is 1,000 electron volt gamma. So that's going to be the energy of the gamma emission. So it's a not terribly energetic gamma ray. That actually concludes this presentation, and I'm glad I was able to do this in a little bit less time, so you don't have quite as much to absorb for this next test. In the next chapter, though, we're going to go into delve a little bit more heavily into radioactive decay. Your book calls it the gory details. It's not too gory, I hope, but as I said, the things that are most important in this chapter are these decay diagrams, and I'll probably give you a problem or so involving, maybe you'll have a problem where I'll give you all the masses, and I'll have to actually have you calculate the either the binding energy and or the energy of maybe a photon that's being given off, or certainly I ask you to calculate the mass defect in some cases. So again, thank you for your attention, and I wish everybody hatzlacha on the next exam.